Hello everyone, welcome to AVLSI lecture number 14, part 2. And today we are going to continue on discussion on source follower circuits. So let us begin. So here we have our first numerical. So for the circuit shown in figure number 14.2.1, which is over here, and W by L of 1 is given 20 by 0.5. I1 value of the current source is given as 200 microamperes. VTHO is given as 0.6 volt. Twice phi f is 0.7 volt. VDD is 1.2 volt. Mu and Cox is 50 microampere per volt square, and gamma is 0.4. Okay, so we have to calculate the V out for V in equal to 1.2 volt. Okay, so we have to calculate the value of V out. And the second part is that if I1 is implemented as M2 in the transistor, that is your NMOS current source load, we have to find the W by L of the NMOS transistor, M2 transistor, for it to remain in saturated when Vin is equal to 1.2 volt. So that's a separate part, but let us try to concentrate on the first part, that is calculating the V out value for Vin equal to 1.2 volt. So let us begin. Now, since I1 is the constant current source, the current flowing into the MOSFET ID1 also will be constant, equal to I1. So for a source follower, we know that your M1 transistor is in saturation, correct? Your M1 transistor is in saturation. So the drain current formula will be ID1 is equal to, so ID1 will be equal to half mu n Cox W by L of 1 into VGS minus VTH the whole square. Okay. So elementarily, actually speaking, your M1 transistor is suffering from body effect. But for the first case, we will directly use the formula, value of VTH as it is, and next in the next iteration, we'll calculate the value of VTH for body effect, considering the body effect. Fine. So from this figure, what is my VGS? So VG is actually V in, and VS voltage is actually V out. So your VGS is nothing but V in minus V out. And we are assuming initially that VTH1 is actually VTH, not VTH1. Let me just make it as VTH. So VTH is equal to VTHO, which is equal to 0.6 volt initially. And then we calculate the value of ID1, right? So ID1 will be half mu and Cox W over L of 1. Instead of VGS, we'll substitute V in minus V out minus VTH the whole square. And from here, for V in equal to 1.2 volt, we have to calculate the value of V out, right? So we take this V in minus V out minus VTH the whole square on this side, and rest all the terms on the other side. So we on the right hand side, we get equal to twice ID1 divided by mu and Cox W by L of 1. Now mu and Cox value is given, W by L value is given, ID1 value is given as 200 micro. Let us check that. Yes, I1 value is 200 micro, and since it is a current source, ID1 also will be 200 micro. So from here, the only unknown value is V out. So you solve it over here. So 0.6 V out the whole square, 0.6 minus V out the whole square is equal to 0.2. And from here, we get the value of V out as 0.15278. Okay. But remember, this is ignoring the body effect. Now we know that the threshold voltage will change with body effect. So we'll calculate the original value of VTH. So VTH will be equal to VTHO plus gamma into square root of twice phi f plus VSB. Okay. And minus of VSB1 actually, minus of mod of twice phi f. So see, twice phi f value is available. Even the gamma value is available. Even the VTHO value is available, right? But VSB1, what is VSB1? Let us check that from the circuit diagram. So VSB1, your body voltage is connected to ground. Your source voltage is connected to V out. So what is VSB1? Your body voltage is 0 and your source voltage is connected to V out, correct? So your VSB1 is nothing but your V out value. And V out value, you initially got it from the previous iteration, correct? So from here, we can recalculate the value of VTO, VTH, which will be VTHO plus gamma into square root of mod of twice phi f plus V out minus of square root of twice phi f, right? So we plug in the values over here. VTH value is VTHO value is 0.6, gamma value is 0.4, twice phi f value is around 0.7, that is given, right? Let us check that. Twice phi f value is 0.7. Yes, indeed it is 0.7. So we plug in the values in the calculator. V out value from the previous case is 0.15278, correct? We plug in the values over here and we'll find that your VTH, because of the presence of your body effect, is coming out to be 0.6347, right? And it will definitely be greater than 0.6, correct? Which is greater than your VTHO. So this is a correct estimate. VTH value should be greater than your VTHO value. Now we again recalculate the value of V out. So we already established the relation between the V in minus V out minus VTH the whole square is equal to twice ID1 divided by mu and Cox W by L of 1. So over here we calculate, plug in the value of VTH only new. Rest all the things will be same. So after algebraically solving it, you will definitely get the value of V out as 0.1181 volt. Okay, so that's the value of V out when V in is equal to 1.2 volt for a source follower with current source load. Okay, so let me quickly revise it, what we have to do. So for this circuit shown over here, we have to calculate the value of V out when V in is equal to 1.2 volt, right? Now, since it is a source follower, we write the equation of ID1 and we found out that VGS is equal to V in minus V out. And initially we assumed that VTH is equal to VTHO. So we calculated the value of V out. From here we got it as 0.15278. Then because your transistor is suffering from body effect, we have to recalculate the value of VTH, right? Your VSB1 came out to be same as V out. So V out from here we substituted in this formula value and we recalculated the value of VTH. And finally we recalculated the value of V out with the new value of VTH. And we finally got the V out value as 0.1181 volt. So this completes part 1 of the numerical. Let's move on to part 2. So part 2, what it says is that your current source load I1, current source I1 is implemented as M2 in the figure number 14.2.2. So we have to find the aspect ratio or W by L ratio for a second transistor M2. Provided your M2 remains in saturated when V in is equal to 1.2 volt. Okay, so for this circuit we have to determine the value of W by L of 2. So let us begin. So since I1 is replaced by M2 as a current source, your M2 is the current source load, which is always in saturated mode. So over here, what is the value of V out earlier? Because we have replaced, right? So we have replaced the earlier one, right? We have replaced the I1 source with current source load. So we'll use the value of V out obtained from the previous result. And from the previous result, we have V out equal to 0.1181 volt and ID1 was equal to ID2 was equal to 200 microamperes from the previous result. Fine. And now, since we have replaced this current source with a MOSFET, the VDS2 for the second transistor M2 transistor will be same as V out. So VDS2 will be 0.1181 volt. Fine. So now the condition for M2 to be in saturation is that VDS2 should be greater than or equal to VGS2 minus VTH. VTH2 actually we should have written, but the threshold voltage we have kept it same for both the transistors. So your VDS2 is nothing but your V out. So for the condition to be at the edge of saturation, V out will be equal to VGS2 minus VTH, and which is given as 0.88181 from the previous result we have calculated. Now, since M2 transistor should be remaining in saturation, the drain current formula will be ID2 is equal to half mu and Cox W by L of 2 into VGS2 minus VTH the whole square. So from here we calculate the value of W by L of 2. Here ID2 value is same as 200 microamperes. Mu and Cox is 50 micro. VGS2 minus VTH. So from here we can see V out is equal to VGS2 minus VTH, which is 0.1181, which we evaluated from the last part. So from here all the values are available now. And finally, we get the value of W by L of 2 as 287 divided by 0.5, which is coming out to be approximately 574:1. Okay, so that's the value of W by L of the second transistor. Now, why we are writing it as divided by 0.5? See, W by L of 1, it's also in the same form, 20 divided by 0.5, and normally we keep the length as same, ratio will be same. So hence we are converting this also as W by L of 2 as 287 divided by 0.5. Okay, so let me quickly revise this numerical and then we will proceed. So what we are doing over here is that we are replacing the I1 current source with the MOSFET, M2 MOSFET. Okay, now we have estimated the value of I1 from the previous result. We'll start from there only, right? And now, wait a second. Yeah. So see here, Vin was equal to 1.2 volt. That means I1 won't change. So I1 was nothing but your ID1 or ID2. In this case, both the currents flowing in the transistor M1 and M2 will be same. So your ID1 is equal to ID2 is equal to 200 microamperes. Vout was calculated from the previous result. And we found out that Vout is equal to VDS2 for M2 transistor, right? And we wrote the condition Vout should be equal to VGS2 minus VTH, which was 0.1181. Now we have written the formula for drain current. From there we isolated the term of W by L of 2. We have all the values of result. VGS2 minus VTH was 0.1181 square, right? And we finally got the value of W by L of 2 as 287 divided by 0.5. Okay, so if you have any queries, you can let me know, or else we can proceed. I'll wait for a few seconds over here. If you have any query, you can add it in your comment section. If no, we will proceed to the next part. Okay, so let's proceed to question number 2. So for question number 2, we have to calculate the voltage gain of the circuit shown in the figure 14.2.3. Fine. Now, if you look carefully, in your 14, what is we have to identify the circuit first. So basically, it's a source follower because input is applied to the gate terminal, output is taken from the source terminal for M2, M1 transistor, and M2 transistor is acting as a NMOS current source. Okay. Now, and we have a RL connected in parallel with the output. Now we have to find the voltage gain not by deriving the entire, first by deriving by the traditional approach. No, we won't do that. What we will do is we'll write the voltage gain expression by inspection. So let us try to do that. We know if a transistor is in saturation, will be modeled by, and VB value is given to make sure that this MOSFET M2 is in saturation. So if a MOSFET is in saturation, it can be modeled by RO2. I mean the output resistance RO2, right? Because that is what is representing the MOSFET as a current source, correct? So here what we will do is we'll draw the small signal model only for M1, right? And M1 is suffering from body effect, correct? So here we have GMB12. Here also it should be GMB, not that GMB term is missing. Let me add that from here. Okay, wait a second. So here we will have, sorry, we'll remove the term of GM and we'll add GMB1. Okay, GMB1 into VBS1. Yeah, now it's absolutely fine. So what are we doing over here is that we are trying to make the small signal model for M1 transistor, and for the M2 we'll just replace it by RO2 because it is behaving as a current source, right? So we can replace it by a RO resistance, in this case RO2. So input is connected between the to the gate terminal of transistor 1. Between G1 and S1 we have VGS1, it's open circuit. Between the drain 1 and source 1 we have GM1 into VGS1 current source. We also have the RO1 because it will have your channel and modulation parameter. Lambda is not equal to 0, in fact. And we will have the third element in the form of a current source again, GMB1 into VBS1. This is because the body effect is present for M1 transistor. Okay. So for this circuit, we have to determine the ratio of V out upon V in. Now, don't try to solve it by traditional approach. We'll solve it by analytical approach. Okay. So if you look carefully in this transistor, the drain terminal is connected to ground. Okay. And over here, this resistor RO1, it's connected between the source terminal and the ground terminal. So that means RO1 will be in parallel with your RO2 resistor. Correct? So that's what exactly we will do over here. So now if you see carefully, RO1, you have RO1 also in parallel with RO2, and then we have RL also. Correct? So now your circuit gets further simplified, and we can compare this with your this circuit. Now what is this? This is my source follower with a resistive load, and we already derived the formula for this. It was given by GM into RS divided by 1 plus GM plus GMB into RS. So if we found out the effective load resistance between the source terminal and the ground, we can replace this RS by that equivalent resistance. So let's calculate the value of RS. So if you look from the look into the source terminal, we have 3 resistors in parallel. So your RS will be equal to RO1 parallel to RO2 parallel to RL. And you can look at this formula and complete the result now. So AV was equal to GM. In this case, it is a M1 transistor. So AV will be equal to GM1 times RS plus 1 plus GM1 plus GMB1 into RS. And here RS is what? R1 parallel to R2 parallel to RL. So this is how we can write the gain formula by inspection. Now let me keep it steady for some time. So you can have a look. How did we calculate the voltage gain of the circuit shown? So first we have replaced M2 transistor by its small signal equivalent in the form of RO2 because it was working in the saturation region. And then we found out that RO1 is coming in parallel to RO2. And here we have compared it with the standard form of source follower circuit, right? And we calculated the equivalent load resistance, which was actually RO1 parallel to RO2 parallel to RL, and we plug in this formula, and we finally got the expression for the small signal voltage gain without even solving anything, just by inspection. So yeah, so that's the formula of the voltage gain, small signal voltage gain for circuit number 14.2.3. If you have any doubt, you can ask. I'll keep this steady for some time, for a few seconds. Okay, so now let us continue further. So let's move on to question number 3. Again, we have to do the same thing. We have to calculate the voltage gain for the circuit shown in figure number 14.2.4. So over here, they have given explicitly some details are given, right? So what is given? The gate terminal of the second transistor is connected to ground. The source terminal is connected to ground. And actually, this is my the substrate terminal is connected to VDD. Okay, they have given it the substrate terminal or the body terminal of the NMOS transistor is connected to VDD. They have provided this information, right? So we will draw now the equivalent circuit. So we cannot reduce this to your RO2 because, as in the earlier case, because we don't know whether this transistor is in saturation or no, M2 transistor. But definitely this is a source follower, right? So we'll draw the model for the M1 transistor, small signal model, and also for the M2 transistor. So let us begin with the M1 transistor. So first we'll create this. M1 is suffering from body effect, as well as M2 is also suffering from body effect in this case. Both are suffering from body effect. So GM term will come in both the cases, right? Actually, it should have been written GMB2 and GMB1. So here, GMB1 and 2. It should be written over here. Let me see if I can add it. GMB1 and GMB2. So let me add it. Okay, so the changes have been made now. Let us continue our discussion. So over here, for the M1 transistor first, so gate terminal is connected to Vin. The source terminal of M1 transistor is connected to the drain terminal of M2 transistor, right? And from the drain 1 to source 1, we have GM1, VGS1, RO1, and GMB1 into VBS1. And the drain terminal is connected to the ground. Drain 1 terminal is connected to the ground. Now let's talk about source 1. So source 1, we have the output terminal coming out, and that is given to the drain terminal of the second transistor. Now for the second transistor, gate 2 is grounded, source is also grounded. So between the drain 2 and source 2, we have GM2 into VGS2, and we have RO2 also, and we have GMB2 into VBS2 also present over here. Now, if you look carefully for this transistor, we can draw the impedance offered. We can write the impedance offered by the GM2 VGS2 source, current source, which will be 1 upon GM2. We have seen that earlier. Similarly, for the current source GMB2 into VBS2, we can write the equivalent impedance or the resistance will be 1 upon GMB2. Okay. So with this in mind, and RO1 also coming down, right? So here you can see source terminal, it's connected to V out, other terminal is connected to ground. Same is the case with the drain terminal. Drain terminal is connected to V out terminal, other terminal is connected to ground. So this RO1 also will come in parallel. So this circuit over here above, you can, upper part will remain the same. In the lower part, we will have RO1 down parallel to RO2. So as you can see, we have RO1 and RO2 in parallel. Also, we have, this is GM2 into VGS2, correct? And here it is replaced by 1 upon RO, 1 upon GM2, right? So that means we are representing it in a form of a resistance. So here it is 1 upon GM2. Here it will be RO2 parallel to RO1. And for this, we will have 1 upon GMB2, correct? So again, this circuit has become a little complex, but no need to worry, no need to derive it. We'll compare it with the standard form of source follower, wherein the formula will be GM into RS divided by 1 plus GM plus GMB into RS. So you have to just find the equivalent resistance, load resistance RS over here. And if you can see, the equivalent load resistance over here RS will be 1 upon GM2 parallel to RO2 parallel to RO1 parallel to 1 upon GMB2. So this is my value of RS, and that we plug in into the formula because remaining is my source follower. So your gain AV will be GM1 times RS divided by 1 plus GM1 plus GMB1 into RS, which is this huge term over here. RO1 parallel to RO2 parallel to 1 upon GM2 parallel to 1 upon GMB2. So if you analyze the gain, small signal voltage gain by inspection, you will save a lot of time, because deriving and arriving at this result by traditional approach will take you around half an hour. Okay, roughly, by solving all the steps and all that and putting it, not half an hour, maybe max to max 15 minutes or 10 minutes, correct? So by gain by inspection method, we have to just draw the small signal model, and wherever possible, you can approximate, the resistance offered by the current source will be 1 upon GM2 and 1 upon GMB2. Now, next question will be why we have not done over here, why we have not written over here 1 upon GM1, 1 upon GMB1, right? Because we have already have the result for that in this form, right? That is why we are not doing it for the M1 transistor. We are doing it for the M2 transistor, because we just want the value of RS, and we got the value of RS as the parallel combination of 4 things: RO1, RO2, 1 upon GM2, 1 upon GMB2. So this is how we can evaluate for any circuit, source follower circuit, the voltage gain formula, the expression, just by inspection we can write. Okay. So this is a very useful technique. Please learn it as quickly as possible. Try to practice this on your own, and then try to realize whether you are arriving at the same result or no. So I guess that is all for this session. So today we have completed one numerical on source follower circuit, and then we have solved two numericals analytically, not numericals, actually kind of derivations for the voltage gain for a circuit given, which is a source follower with some minor details changed, right? And we have written the formula for the voltage gain just by inspection. without deriving any simple step. Okay, so that is all for today's session. Next time we will continue with numerical on the source follower. So until then, have a good day and thank you.